So we're going to talk about linear speed, angular speed, and then some applications. So first let's talk about linear speed. So this can be given by a few different formulas. So we can think of this as speed equals distance over time, or v equals s over t, where s is arc length traced by a point P at a time t. So just to give you a visual of this v equals s over t. So you've got this point P moving along this circle, right? So you've got your s is your arc length from here to here. So that's kind of how you can visualize that. So places where we might use something like linear speed. So we're talking about speed as we're moving along a circle. So a lot of times you can have like gears or pulley problems, so moving along those tracks, or maybe like a car moving along a curved highway. So you're thinking about moving along a circle and what the speed might be in those types of situations, like circle or disc or something. Okay, so let's also talk about angular speed. So this is given by the formula. So this is omega equals theta over t, where theta is, of course, in radians. I want to make one little note here. It's a little hard with my handwriting to tell, but that is omega. So it's the lowercase Greek letter omega. It's not a W, so you want to make it a little bit fancy. So whenever you have some of the fancy Greek letters, take a little pride in making them look nice and making them clear. So this looks fancier than my normal W. That's kind of how I try to denote it. Omega is one of the harder ones for me, honestly, because my handwriting's a little curved. Okay, so anyways, so where would we use angular speed? So really whenever we want to measure how fast the angle is changing, so you have your initial side and then you might have a terminal side that is moving along the unit circle. So how that angle would change is when we would use angular speed. And we'll see some examples of that in this video. So we can connect these two formulas. So we have v equals s over t. We talked about that. So remember, S stands for arc length. So remember arc length, that was r times theta. So if I were to make that substitution, rewriting it this as r theta over t, so just substituting this in, I can be a little clever and rewrite this formula as r times theta over t. So just kind of break up the fraction like that. And so now what you might notice is that we have angular speed. So remember, omega is theta over t. So it's this part right here. So another way that I could actually write out linear speed is r times omega. So we have a couple different ways to express it actually. Okay, so the first thing I want to do is just kind of get you used to working with these formulas and writing them out. So I have some just really basic kind of really like algebra questions for using the formula omega equals theta over t to find the missing variable, just to kind of get you used to the placement of things, and then also working with the units a little bit. Now, if you're struggling with this, like with what units to use, I would recommend that you actually write the units out and use dimensional analysis. I tend to skip over that. But that could be a helpful thing to do. Like once you get used to what units you need, you'll probably remember it, but at first you might want to use dimensional analysis. Okay, so anyways, so I have my omega is going to be pi over 3. I don't have a theta. And then my t is going to be 6. So I've filled all this in, so I need to solve for theta. So to solve for theta, of course, I'll just multiply both sides by 6 and make my cancellations to get that theta in this case would be equal to 2 pi. And then just to get a little bit more practice with this formula, so if I had something like theta, if I have my theta is given and my t is given, well, in this case now I can just plug these straight into the formula. And so in this case, if I go through and do this, so I'll do 3.721 radians divided by 18.34 seconds. And that gives me 0.2029 radians per second. Now, one thing I do want to point out here, with this theta equaling 2 pi, this is clear, like because this is theta, we know this is an angle and we don't have like a degrees listed here. This is like kind of assumed that this is already radians, so we don't have to write that out. But in this other answer that we just found, this we need to clarify the units on this. So you do want to actually have, whenever you have a rate, you want to write out what that rate is. So just a note there. Okay, so let's just play around with a few more of these formulas. So let's use, how about V equals R times omega? So let's try that. So if I have my R, so my R is going to stand for a radius, so that's going to be 10 meters. And then let's say my omega is 9 pi over 5 radians per second. So when I multiply these things together, so I've got 10 times 9 pi over 5, and this will simplify to just 18 pi, and that comes out to meters per second. So you might be thinking, what happened to the radians? So I've talked about this before. Radians are not, they're not a measure in like the way that the radians are not, they're not like centimeters, they're not like feet. So when you multiply something like meters times radians per second, you can just drop the radians and then let that length take over, I guess is what I'm getting at. So that's what happened with that. So I have one other example here. So maybe you want to take a second just to try this on your own and see if you can figure out what you think the units might be. Hit play when you're ready. So I've got my V is equal to 10 meters per second, and my omega is 3 pi over 2 radians per second. So if I plug those in, so what's going to end up happening here is, so I get R equals 10 times 2 over 3 pi, and this will come out to being just meters. Now, the reason for that is you're really, like, since you are dividing, so one of these things per second by another thing per second, the set per second drops out, so you're just left with that length of meters. And so in this case, this would equal 20 over 3 pi meters. That would be how that simplifies. Okay, so let's take a look at a few problems now that can come up with this. I've got a variety of these. So suppose a point P is on a circle with the radius equal to 5 centimeters, and then the ray OP is rotating with an angular speed of pi over 10 radians per second. So first I want to find the angle generated by P in 3 seconds. Okay, so in this case, I've got my formula, so omega equals theta over T. And so I have, let's see, I have my angular speed, right? And then I have my time. So I can just plug those pieces in. So it might be a little bit better in some ways. I could rewrite this as theta equals omega times T, so just to make my life slightly easier. And then I can multiply those things together. So pi over 10, that was my angular speed, and then the 3, which was the given in the problem. So this will come out to 3 pi over 10 radians, because the seconds will end up canceling themselves out. Again, use dimensional analysis if you need to figure that out. Okay, so part B, find the distance traveled by P along the circle in 3 seconds. So now what we're talking about, the distance that P has traveled, we can really just think of that as arc length. So we've got this point P and it's moving along a circle, and so I want to know how far has it traveled. I figured out what theta was, and I know the radius. So since I know the angle that was generated in that 3 seconds, I can just use that angle with this arc length formula. So in doing that, this will come out to 5 times 3 pi over 10. So I just reused the answer that I had before. And so this will come out to 3 pi over 2 centimeters. And then finally, find the linear speed of P in centimeters per second. Okay, so now linear speed. So we have a couple different formulas for that. I already know what omega is, so I want to use this as R times omega, because then I can just plug everything in, and this just becomes 5 times pi over 10. And so this comes out to pi over 2 centimeters per second. Okay, so playing around with these formulas just a little bit more. So we know that omega equals theta over T. So I could actually rearrange this like we just did, right? Theta equals omega times T. Okay, so let's play around with this a little bit. So what if I took this theta and now replaced it into my arc length formula? So what I mean is I'm going to take this part here and I'm going to substitute it into my theta. So I get this new formula now for arc length, R times omega times T. So it's just a new way to think about arc length, and we're bringing like angular speed into it. So let's use that formula for a second just to kind of play around with it, and again playing around with the units. So I'm going to challenge you here to pause the video, give this a try, hit play when you're ready, and remember to think about what your units will be. Okay, so I multiply these together and I get 5 times 2 pi over 3 times 8. Okay, so in this case, my seconds are going to drop out, so I'm just left with my centimeters. So when I multiply these all together, I get 80 pi over 3 centimeters. Okay, so one more just to play with. So again, I would recommend that you pause the video here and then hit play when you're ready. So if I plug these in, so I get 3 pi over 2 equals 4 times 3 times omega. So to solve for omega, then I can just take that 3 pi over 2. So 4 times 3 was 12, so I can just divide this by 12. So dividing by 12 is the same as multiplying by 1 over 12. Okay, so in this case, with what I'm dividing by, so my kilometers are going to end up dropping out. So I'm just left with really radians per second. So this comes out to pi over 8 radians per second in this case because my kilometers dropped out. So then I can refer back to my radians. Okay, and so I have a handful of application problems related to this, so I wanted to do one in this video. I have another example video where I do a bunch of these. Okay, so let's talk about this one though. So the orbit of the Earth around the Sun is almost circular, so suppose that the orbit has a radius of 93 million miles. We know that a year is 365 days, so find the angle formed by the Earth's movement in one day. Okay, so we're talking about an angle, so that's theta. We need to remember the orbit is circular, so if I go all the way around the orbit, since it's a circle, going all the way around would come out to 2 pi. So if I want to know what is the movement in one day, there's 365 days in a year, that's going to be 1/365th of 2 pi, which means I multiply those two things together. So my theta in that case would be 2 pi over 365 radians. So next we want to give the angular speed in radians per hour. So we're going to use omega equals theta over t. That's our formula for angular speed. Now we already found theta in the first part of this problem, and then we're talking about hours. So how many hours are there in a day? 24. So I could divide by 24, or equivalently I could multiply by 1 over 24. So that's just what I've written down just to make it look nicer. So this was the theta that we just found, and then I'm going to divide by 24 or multiply by 1 over 24th to get my omega. And so this comes out to, when I multiply everything together, this comes out to pi over 4,380 radians per hour. Okay. Now here's the cool part of this problem. Now we want to find the linear speed of the Earth in miles per hour. So how fast does the Earth move along its orbit in 1 hour? We've actually done all the work to figure this out. So linear speed, we know one way we can use it is r times omega. We found omega in the last part of this problem. That's why we want to use this formula. And then my r is given here, that 93 million miles. So I can multiply this by the omega that I found. And so this actually gives me then the hourly speed that the Earth moves. The Earth is traveling at a rate of 67,000 miles per hour. Pretty crazy, right? You probably never really think about that. Okay, and so that brings us to the end of this video. I have many more examples of applications with these types of problems. So I'll drop a link to that in the description. And otherwise, thanks for watching, guys. I'll catch you next time.